Hey guys, welcome back to my channel. In this video, I'm going to be going over all of topic 1. So that's stoichiometric relationships in IB chemistry. So in topic 1, I'm going to be going over topic 1.1, 1.2, and 1.3. And as of course, as you know, topic 1 does not have a HL component. So it's just going to be this topic 1 component, which applies to both SL and HL. I'm going to be using this syllabus guide, that's the official IB syllabus guide, and I'm going to be going through it and explaining mainly the understandings. I won't be covering international mindedness because you're probably not going to be assessed on that, and you're probably, if you're watching this video, you're probably in a hurry to do an exam, so I'm not going to waste your time with this stuff. Also, theory of knowledge, I'm not going to be linking to that at all. In terms of guidance, I will go over that. Utilization, yes, I will. And syllabus crosslinks, I won't go through that. Aims, I'll go through slightly. Okay, so without further ado, we starting with topic 1.1, which is introduction to the particular nature of matter and chemical change. So we're looking at how microscopic changes, maybe even nano size changes. So we're looking at atoms and subatomic particles and how their interactions lead to chemical change. So we're looking at the world and its changes, its chemical changes from the smallest available length. So first we're going to look at atoms. Atoms are different elements combined in fixed ratios to form compounds, which have different properties from their component elements. So an atom is the smallest subunit of an element that retains its characteristic properties. So an element is a pure substance. So there's hydrogen, helium, lithium, beryllium, etc. in the periodic table, which you will have access to. And when different atoms combine, they can combine in fixed ratios to form chemical compounds. And compounds, what's cool about them is that they're distinct from the individual particles. In contrast to compounds, we have some things called mixtures. So mixtures contain more than one element or compound and are not chemically bonded, and so retain their chemical properties. So when you have mixtures, you can have either homogeneous or heterogeneous. Homo means same, hetero means different. So homogeneous means same state. So mixtures could contain a same state of compounds. So like a heterogeneous would mean different states. So an example of a heterogeneous compound would be mud. In mud, you have water, sand, dirt. They aren't chemically bonded to make a mud compound, it's a mixture, right? But then they're different states as well. So you have the dirt particles suspended or moving around in this watery liquid, right? So you have a solid and a liquid, different states, boom, heterogeneous. And mixtures can be one element and another element together. So mixtures could contain like chlorine and oxygen. I'm not sure if that's real, but I'm just using that as an example. And they won't be chemically bonded, but they will be together. So they'll be in one mixture, even though they don't have their their atoms chemically bonded. So chemical bonding is what leads to distinct properties, and chemical bonding does not happen in mixtures, which is why you retain the characteristic individual properties of elements. So individual properties are retained in mixtures. So applications, deduction of chemical equations when reactants and products are specified. The chemical equations are quite straightforward. You probably covered this already, and what you need to remember is balancing equations. It's quite straightforward. You just need to match the number of atoms on each side of the equation, so the reactants and the products. State symbols, you have solid, liquid, gas. Aqueous, solid means solid state, liquid. Liquid state, gas, gaseous state. Aqueous means in water. And what's the only difficult part about this is liquid and aqueous. If you have pure water, you'd say liquid. If you have aqueous substance, water can't be aqueous because aqueous by definition means in water, and water in water is just liquid water. But if you have like sodium chloride in water, you call that aqueous. However, if you have sodium chloride in a liquid form, such as in a pure electrolytic cell, you're going to have a liquid sodium chloride. Well, we'll look at that later when you're doing topic 9. Explanation of observable changes in physical properties and temperature during changes of state. So when state changes occur, you're generally going to be looking at solid to liquid to gas in terms of increasing movement between particles and space between particles and less order. So in a solid state, all the atoms are packed together tightly and they do not move around a lot or vibrate much. However, when you move into a liquid, there's a bit more movement, there's more space, less attraction that's holding the particles tightly packed. And when you talk about gases, all the intermolecular forces have been broken. We'll talk about intermolecular forces later. And you have lots of space between particles and high speed. So you're going to have to consider how these physical properties change with increasing temperature. So particularly increasing temperature leads to solid to liquid to gas. Balancing equations should be covered in various types of reactions. So balancing equations is quite straightforward. I mentioned earlier. Just do a bit of practice. Names of changes of state. Melting is from solid to liquid. Freezing is from liquid to solid. Vaporization is from liquid to gas. Evaporation and boiling is a subset of vaporization. Condensation is gas to liquid. Sublimation is a gas is from solid to gas without going into liquid state, and deposition is when gas becomes a solid without turning into a liquid. Those last two are quite interesting. Next up, we have refrigeration and how it's related to changes of state in the utilization part. So in refrigeration, we have this liquid called refrigerant, and in the refrigerators in your house, what happens is there are pressure changes that are applied to this liquid. And based on pressure changes, you can actually change the state of this refrigerant. And when changes in state occur, you have changes to the actual intermolecular, the forces between the atoms or molecules in that refrigerant. And this induces a temperature change. And this temperature change does not only occur in the refrigerant, but on the environment in the refrigerator itself, thus cooling the refrigerator or the refrigerator environment. So changes in pressure in the refrigerant liquid can lead to changes in temperature in the refrigerator, allowing a cooling effect to be produced. Atom economy is this formula about useful products to all reactants used, and you have to multiply that by 100, not 10, because it's a percentage measure. And freeze drying of food is something you should look up. It won't really be assessed that much. Next up, we have latent heat is not required. Physics students would know what that is. I have no idea what that is. I don't study physics. Names and symbols of elements are in data booklet. That's the periodic table, I believe. But yeah, so you don't have to memorize the names essentially, but just know like the first 20 names of the periodic table. It's not that hard. Next up, we have topic 1.2. We're talking about moles. This is where real stoichiometry and calculations begin. The mole is a fixed number of particles and refers to n of a substance. Mole can be defined as the number of carbon 12 atoms in 12 grams of carbon 12. So that's called Avogadro's number. Sometimes masses of atoms are on a scale relative to carbon 12. Explain the relative atomic mass and molecular mass. So relative atomic mass is the mass of an atom in terms of these atomic mass units. Molecular mass is the mass of a molecule. Molar mass is the units grams per mole. This is important because when you're doing calculations, these can cancel out. Empirical formula and molecular formula. Empirical formula shows the lowest common ratio of of atoms in a molecule, whereas the empirical molecular formula shows the actual number. So for example, you could have this as the molecular formula. Sorry, empirical formula, but the molecular formula could be this. So empirical formula is used to show ratios, whereas the representation of reality is with the molecular formula. When you calculate molar mass of atoms and ions, etc., you're going to have to use the periodic table and use the relative atomic mass to um, calculate all these molar masses. So with a molecule, if you have two sodiums and an oxygen, you need to add up the atomic mass units of sodium times 2 plus oxygen to get the total molecular mass. Solution of problems involving relationships between the number of particles, amount of substance in moles, and mass in grams. So you just need to remember N equals mass over molar mass. So number of moles equals mass over molar mass, and if you learn to utilize that formula, you'll be able to comfortably do all stoichiometry. Interconversion of the percentage composition by mass and the empirical formula. So that's just talking about percentage composition by mass. It's just to do with questions where you're given like, okay, this molecule has like 60% carbon, 20% oxygen, 20% hydrogen, and you're meant to deduce the empirical formula. And this is also another type of question you have to do. So just do a couple of these questions. Your teacher would probably provide you with them. But essentially, my idea for these is to construct a table, and you'll be able to calculate the molar ratios of each one. And then after you do that, you got to determine the molecular formula by considering what multiple of the empirical formula gives the correct molar mass of the molecular formula. Say the molecular formula had a molar mass of 120 and your empirical formula had a molar mass of 30. Well, you know that there's probably going to be 4 times the empirical formula to get the molecular formula. So, say for example, you have 2C2H6. Okay, that doesn't work. But let's say you had COH2. Okay, that's your empirical formula. That should add up to, yeah, that adds up to 30. But if your molar mass is going to be 120, then you're going to make all this 4. So it'll be C4O4H8. That's going to be the actual molecular formula. That's how you convert from empirical to molecular formula using molar mass. Obtaining and using experimental data for deriving experimental formulas involving mass changes. So when you look at a mass change, you can see if you have a reaction occurring and you have, say, you have 6 grams lost, and then you know that's relevant to the carbon, you could deduce the amount of carbon in a molecule. And you can use this once you solve for one atom, you can go for the other atom, and etc. You can work your way through until you deduce the entire molecular formula. That point is actually a bit difficult, so I'm going to highlight that. That's probably going to be a whole other video I'm going to make. So I'm just going to put a highlight there. That's kind of hard to explain in a quick video like this. Guidance, the value of the Avogadro, yeah, so the number 6.02 times 10 to the power 23. That's the Avogadro's number, and it's given in the data booklet, so you don't have to memorize, but you sort of get used to it, and after a while you just remember. The generally used unit for molar mass, yeah, so SI unit, we mentioned this earlier, just remember that one, because sometimes if you like to use units in your calculations, you need to make sure the units cancel out, and it's a good way to check whether your answer is correct or not. Moving on, you have topic 1.3, reacting masses and volumes. Reactants can be either limiting or excess. So limiting reactant is the one that we have less of and determines the overall number of products. So if we have, let's say, 1 carbon and two hydrogens, sorry, 1 carbon plus 2 hydrogens. Let's say we had this equation, so hydrogen gas and chlorine gas to form hydrochloric acid. It may not happen in the real world, but just as an example, so if we have 0.1 moles of hydrogen gas and 0.2 moles of Cl2, well, we're going to have all this H2 reactant, and we're going to have excess or spare Cl2. So this is the reactant in excess, this is the limiting reactant, and the final amount of products we make will be 0.1 times 2 based on the coefficient, so it will be 0.2 moles of this, not 0.4, because we cannot react all of this because this is the excess. So the limiting reactant is important in our calculations to identify so that we can determine how much product can be obtained. So experimental yield is how much you expect to make of a product theoretically. How much you actually make of a product. Theoretical yield is how much you expect to make of a product based on stoichiometric calculations. Generally, these are different because you lose products, and you have this measure called percentage yield, which is just experimental yield over theoretical times 100, and this is a measure of how much product you actually obtain based on how much you expect as well. Avogadro's law enables the mole ratio of reacting gases to be determined. So Avogadro's law states that equal volumes of gases at the same temperature and pressure have the same volume. So you're going to have to use this to determine the volume of gases. So what we're meant to say is if we have 1 mole of hydrogen gas to 2 moles of chlorine gas, that means if we have 1 liter or 1 cubic decimeter of hydrogen gas, we're going to have 2 cubic decimeters of chlorine gas. So the ratios in the stoichiometric formula apply to the gases as well. That's kind of a convenient way for us to find the volumes of gases. Mole volume of an ideal gas is a constant at specified temperature and pressure. So that's what I said earlier about Avogadro's law. That's just a different way of stating it. The mole concentration of solution is determined by the amount of solute and the volume of solution. So concentration equals moles over volume. So you express like 0.1 moles per cubic decimeter. Notice how the units match up: volume for decimeter and moles for number of moles. In chemistry, C equals N over V is quite an important formula when it comes to titrations and much of the maths you're going to do in future. A standard solution is one of known concentration. Just remember that if someone mentions or something mentions a standard solution, we're talking about something we know the concentration of. Solutions are problem relating to quantity excess. Yeah. So this is just basic stoichiometric calculations, reactive volumes of gases using Avogadro's law. So just remember, if you have same temperature and pressure, you're going to have the same volume of gas, given that the moles are the same. But if you have 1 mole of gas and 2 moles of gas, then the volumes are going to be 1 to 2 respectively. The solution of problems analysis of graphs involving the relationship between temperature pressure. So just this is another video I'm gonna have to make. So it's just the shapes of the graphs, but it's kind of intuitive. So if you think about Boyle's law, Charles' law, and etc. So Boyle's law states that pressure is or volume is inversely proportional to pressure. Charles' law states that volume is directly proportional to temperature. If you understand proportionality, you can be able to draw the graphs. But generally, you won't be asked to draw the graphs. You just have to uh, probably have a. It's probably going to be a paper one question where there's multiple choice, and you have to pick the graph that corresponds to the relationship. So it'll ask something like, which of these graphs shows the relationship between temperature and pressure, and you'd have to pick the appropriate one. Solution of problems relating to ideal gas equation, that's PV equals nRT. Cool thing about chemistry, you don't have to memorize much. You literally have this in your data book, but pressure times volume equals moles times ideal gas concentration times temperature. Temperature is in Kelvin. And in the ideal gases, they're actually an assumption of reality. So in the ideal gas concept, we actually assume that gases are gases consist of tiny particles which have no attraction to each other and consist of negligible volume. They move randomly, and they do not make noticeable interactions with each other. So what happens is we're assuming something that's not true in the real world, and when we have low temperature and high pressure, gas molecules become super tightly packed, and their intermolecular forces become a bit tighter, right? And because of this, we actually differ or divert from the ideal behavior model, and we're going to get some results that are a bit different from the ideal gas equation. But you won't have to know how to make calculations with the adjusted gas law. Um, so sometimes you're going to be given results from an experiment, and you'll have to use that to get an answer from the ideal gas equation, and that's just substituting in values. So again, this is just working with concentration and that formula. So titration is a method where you add a substance of unknown concentration into a substance of known concentration, given that these two substances react together, and based on how much of the unknown concentration substance you add to the known standard solution, then you can determine the concentration of that unknown concentration substance. So it's a way of determining concentration, and I'll make a video on that later. This is kind of hard to explain if you haven't heard of titration, but most likely you have. And given the purpose of this video is to act as a refresher before an exam, um, I'm not going to go over that. Values for the mole volume of ideal gas, I quote, yep. So you're gonna have to remember 22.7 in standard temperature and pressure, and room temperature and pressure you need to remember 24.8. The ideal gas equation, there you go, and the value of R, the ideal gas, the gas constant is given, it's like 8.31. Um, Units of concentration, grams, yeah, so parts per million is the only hard one. These are quite straightforward. Grams per cubic decimeter is not really used. It's mainly this one in chemistry you're gonna have to be familiar with. Use of square brackets is concentration. So when you have this will come up a lot in topic 8, but if you have H plus and then square brackets, that literally means concentration. So square brackets you need to get familiar with. And other than that, guys, that's going to be it for topic 1 in IB chemistry. And hope you guys learned something new. And was successfully able to revise this particular aspect in order to get ready for your chemistry exam. If you guys want to see more content like this, please like and subscribe. And if you have an urgent topic you want me to cover in chemistry before an exam, please just comment down below and I'll make sure to do it. See you guys later in the next video.